In this video, I'm going to do a quick overview of nuclear decay. So starting off, I want to review the notation of how we write elements. So first, the more common way on the periodic table at least, we'll see is this way here. Um, this element uranium, the symbol is just a letter. I'm going to make this a little bit smaller. The symbol is the letter. The atomic number is how many protons it has, and that's found, the 92 is the atomic number for uranium, and the number of protons is what defines the element. So if it had 93 protons, it'd be a different element, 91 different, right? And then the atomic mass here is the total number of protons and neutrons combined. So the total number of nucleons in the nucleus. This notation here is what we're going to focus on today. It's a lot more common writing equations. So this here is the symbol. The X would be the U, right? So it's the symbol of the element. And then the atomic number here is the number of protons. Atomic mass here is the Z. This would be the 238. And then N is the number of neutrons. So here, let's write number of neutrons. Okay, so remember that, and we'll really use this a lot during this lecture, this video. So why does nuclear decay even occur? We want to talk about that. I want to start off by going over the belt of stability. This right here is the belt of stability. We have a number of neutrons on the y-axis, a number of protons on the x-axis, or the atomic number, right? The A. So as we see, generally, this dotted line here, that's the one-to-one ratio. It represents that there's the exact same number of protons as neutrons. And we find that around 20-ish, 25, the stability gets off of that one-to-one ratio. And this orange, or this kind of pinkish orange in the middle, represents the most stable state for the nucleus. So for example, a nucleus with 50 protons, to be the most stable, would have about 65 neutrons for a total mass of, what is that, 110, right, or 115 atomic mass units. So that'd be the total mass. And as we see, that goes up. What happens though is that as an element, if it gets too many neutrons or too many protons and it's not stable, it's not balanced, then it'll decay, or it'll have parts or particles break off, or it'll emit particles to get back to this belt of stability here in the middle. And we'll see how that works. There are a couple different ways that elements decay, and so we'll find how that happens today. We'll explore that. Periodic table. We're all familiar with this. It just defines all the elements, and we'll refer back to this regularly, okay? But this is essential. This format is crucial to understanding how elements actually decay. As a quick note, I want to talk about neutrinos and antineutrinos. A neutrino, first, we have to understand that we actually don't know a lot about neutrinos. They have almost no mass, and they're not charged. So it's very, very difficult to track down neutrinos and to understand what they are, because they just go through everything. They're not charged, so they're not affected by electromagnetic fields or anything. And then an antineutrino is the antimatter counterpart of a neutrino. So every particle has a counterpart of antimatter. And so the antineutrino is the neutrino's counterpart. And these are both particles that are emitted during decay, during nuclear or radioactive decay. And we'll see in the equations that I'm about to go over, we'll see that those particles are, in fact, emitted. So let's start with alpha decay. Alpha decay, most important is that we have to just understand that a helium atom is emitted. So this is for those huge elements. If you have let's say something like uranium, okay, that we've already taken right here. Uranium is massive. 238 atomic mass units, so 92 protons. So there are a lot of neutrons as well. So it's going to release um, a helium atom to decay to become more stable. So should uranium become unstable or radioactive, it's going to decay, release helium to become more stable. So what that would look like is you have uranium 92, let's see, so 238 here, 92 protons, and then how many neutrons? Let me grab my calculator real quick. 238 minus 92 is 146. 146 neutrons. So that's going to release a helium atom, and it's going to leave, it's going to go back 2 protons, right? So it's dropping to 90. So we have 90 here, and then 232, sorry, that should be 234. So it's 238 minus 4 is 234. That element is thorium, and there are 144 neutrons. Does that make sense how I did that? So 146 minus 2 is 144, and then 92 minus 2 is 90. And 238 minus 4 is 234. So this would be the daughter cell, or the daughter nucleus of the parent nucleus. So that's the result. Okay, moving on to beta decay. We have two types of beta decay. We have beta minus and beta positive or beta plus. So beta minus, you have your original element, and then what happens here is that, or a way to think about it at least, is that a neutron changes to become a proton and an electron. And in that process, an antineutrino is released. So you have your original element. Here you gain a proton, you lose a neutron, so the neutron changes to a proton and an electron, and then an antineutrino is released. So what does this look like? Well, let's take an element like, I don't know, gadinium. Let's take this guy here. So 157, so gadinium, 157, and there are 64 protons. Okay, so we have 64 protons, and we'll go 157 minus 67, whoops, 157 minus 64 is 93 neutrons. So if gadinium, is that what the element is? Yeah, gadinium, were to undergo beta minus decay, it would gain a proton, so we'd be left with 65. The total wouldn't change, and then this would come down to 92, right? So minus 1. And that element, so element 65 is terbium, right? Terbium. Okay, sorry, just double checking that. And then we would have an electron released and an antineutrino. Okay, so that's beta minus decay. Beta positive decay is similar, except kind of opposite. So instead, we have a proton that's turning into a neutron. So we're going to lose a proton and gain a neutron. And then instead of an electron being emitted, because we have a positive charge becoming a negative charge, so we have to, or sorry, becoming a neutral charge, so we're getting rid of a positive charge. So this here is what we call a positron. And it's the counterpart to an electron. And then we have a neutrino that's released. And a neutrino, again, is just that almost massless particle that doesn't have a charge. And this would be the same thing. Well, let me see. Let me just do an example. So let's pick an element, californium. That's where I'm from. Let's pick this guy here, californium. So 251 and 98. So we have, what is this symbol? CF. So we have CF, 251, and was it 98? Yeah, 98. So then 251 minus 98 is 153 neutrons. And that's going to be, it's going to turn into element 97. This will stay the same, which means that there will be 154 neutrons. So what's element 97 is BK, or beryllium. So we have BK here. Positron is emitted as well, and a neutrino. And that's beta positive decay. Electron capture is the same. You get the same result as beta positive decay, except instead of emitting a positron, so instead of emitting a positive charge, you gain a negative charge. So you have the same result, but you gain a negative instead of emitting a positive. So in this same experiment, you'd have californium 98, 251, 153, plus an electron, and that would still turn into BK 251, 97, 154, and a neutrino. Okay, do you see how that's the same result as this, except this is different here. That's the only difference with electron capture. Okay, and then the last form of decay that we're going to cover today is gamma decay. And gamma decay is probably the easiest to calculate, or the easiest to write out the equation, because the element itself doesn't change. So gamma decay, let's pick an element. Let's go holmium. I'm picking all these elements I've never even practiced with. Holmium, 164, let's go 165 and 67. Okay, so we have holmium, 165, 67, which means that there's 98 neutrons, right? And then the asterisk here just means that the element is in an excited state. It has energy stored up in it. So what's going to happen is that we're going to have the exact same element. Nothing's going to change, except that the excited state, the energy is going to be released as gamma particles. And then it just goes on and on. However many gamma particles relates to that amount of, or to the energy state that it's dropping from. So gamma radiation or gamma decay is that a nucleus decreases energy state. So we'll go over, let's just do a quick review of each of them. Alpha decay, you release a helium particle or a helium atom. Beta minus, you release an electron from the nucleus. So a neutron becomes a proton and releases an electron and an antineutrino. Beta positive, you have a proton that becomes a neutron and releases a positron. And then electron capture is the same thing. So you have a proton that gains an electron to become a neutron. You see that? And then gamma decay is that you have an element in an excited state. It goes to the same element, but releases that energy as it drops down to a lower state. Okay, so that is our class or our video for nuclear decay. I hope you understand, and I hope that this was helpful.